Welcome. So this is another part of multivariate, and again, this is like we have f of x as a single variable, but multivariable. You have x1, x2 to like xn. Yeah, that's a multivariable. What we did in a previous part, we looked at parametric equation. We looked at the partial derivative, like these guys, like dy with respect to dx, for example. Here we will look more at the implicit differentiation. Like so, these two are more like math type of things, but the reason I'm covering them because I found them like in the FE exam. So this would be more like a math lesson, basically. Uh, but again, I will recap and just talk about like these three things at the end. But I will show you like here, what I will show you mainly in this lesson, like some of these problems that you solve it with partial derivative. If you found them in the FE exam, you can solve them with partial derivative, but it would be much easier to solve them with implicit differentiation. So let's just finish this quickly, because it's more like math type of thing. Yeah. So implicit differentiation is used when uh, y and x are mixed and cannot be manipulated to give an explicit function. Like I cannot manipulate it to give y as a function of x. So let me show you like uh, uh, let me show you like an example like here. Let me show you an example. What's this guy? Let me get rid of this guy. Just show you an example of what I'm saying. So let's say I have like f of x, y, yeah, is equal to x squared plus y squared minus 25. That would be an equation of a circle. Similar, what we did before was an equation of a sphere. That would be an equation of, sorry, plus here. Okay. Here I can I can get y as a function of x. So I can say basically y squared is equal to 25 minus x squared, and then y is equal to square root of 25 minus x squared. Yeah, that would be like, that will get a, so here I can get y as a function of x. So I can manipulate this function to get y as a function of x. But implicit differentiation is used when you cannot do this. What does this mean? So f of x is equal to x squared plus xy, sorry, xy plus y squared. So here I cannot do this. I cannot get y. I cannot manipulate this function to get y as a function of x. So they are mixed together. Yeah, and in that case, we can still find the derivative for this guy using either partial derivative, for example, or implicit differentiation. But here, remember, partial, like implicit differentiation is just like, I don't want to get you confused. This is just like way of solving equation versus partial derivative. This is a more important concept that you need to know to learn more about what we will be doing next, like in vector calculus or differential equation. But implicit differentiation, this is just like a solution technique. Like so assume like we have like an implicit relationship between x and y through a function this, like f is equal to 0, where y is an implicitly a function of x. We want to find how y is changing with respect to x. Actually, we want to find like yeah, how y, yes, is changing with respect to x. Okay, so like how can we do this? Like How can like we can like so that's like our function, yeah. Like and this function like is equal to 0, yeah. So this would be like equal to 0, and then where is implicitly a function of s, and we can find like the partial, like how can we find like this partial derivative, or even how can we find like not just this partial derivative. So we can find this guy, but how can we find like dy with respect to dx? Like how can I find dy with respect to dx where they are like mixed together? Not just a partial derivative, but total derivative. Let's just apply what we did previously. So remember what we did previously. We say like dx of like my function here, which is like function of x and y, and that would be equal to partial f with respect to x and dx with respect to like dx, yeah, plus, because this guy can go together and you get like your d of x plus partial f with respect to y plus time dy with respect to dx. That would be equal to 0 here, okay? So if that guy is equal to 0, what does this mean? If that guy is equal to 0, I can just like rearrange this term and find like dy with respect to dx. Sorry, this is not partial. This is like dy with respect to dx. So basically like this guy with respect to this guy, that would be equal to what? That would be equal to negative partial f over partial x. This guy will go away, yeah, divided by what? Divided by partial f over partial y. Wow, isn't this like cool? So here I was able to express like my total derivative, yeah, is equal to partial derivative with respect to x minus partial derivative with respect to f over partial derivative of respect to y. And basically I can use this to just solve problems. Similarly, I can do the same. So partial y with respect to partial x, that would be partial, like my function with respect to x and my function with respect to y. Partial z with respect to partial y, that would be partial of my function with respect to y and my function with respect to z. And partial z with respect to x, that would be partial x with respect to z. So like you see, this go here, this go here, this go. Sorry, this is not partial. This is like total derivative. This is a typo here. Okay. This is like not partial. Let me change this also in my main slide. Yeah. So here is this not partial. This is like my total derivative. Yeah. So this is dz with respect to dy, my total derivative here, and this is like my total derivative here, dz with respect to dy. Okay. So again, like this is like in the FE exam. So if you like, I'm telling you like solve this guy using both like the chain rule, similar to like using the chain rule or using implicit differentiation. So we know we can solve this with a chain rule, because here I have basically like I have a function like I have x squared plus y squared minus 25, that's equal to 0. So I can say y squared that is equal to 25 minus x squared. Then I can say y is equal to square root of 25 minus x squared. That's what we did before, like in, remember in lesson 1, the calculus review that we did before, or derivative reviews that we did before. That's like something like this. And then like how could I find like y prime, or like the y with respect to dx? So that would be, again, so I can say, express this like, this is like 25 minus x squared to the power of this. So that would be like, I can bring this guy down, so that would be like half time 25 minus x squared minus half, and then I take the derivative, what is inside the bracket, so that would be 0, and that would be minus 2x. So the 2 here will go away with the 2 here, and what do I get here? I will have an x here, and I will have a square root of 25 minus x squared. Yeah, so I get something that look like this 25 minus x squared. Remember, uh, this is like my y here. Remember, my y is equal to 25 minus x squared, and what see the I forgot the negative, so this is the careless mistake that we do in the exams. So here that would be equal to minus x over minus y. So that is like I solved this guy using the chain rule. That's why I told you I wanted to cover this, because that will help you in the FE exam. So in the FE exam, if it told you find like dy with respect to dx, you will do this like with like follow this procedure and use the chain rule. But if you know like implicit differentiation, you will say, oh, you know what, I have a rule here. I know that dy over dx, that is equal to negative, yeah, see the negative here, partial my function with respect to x over, like see the x go here, partial my function with respect to y. You don't even need to look at, you just remember it, like this guy go here and this guy go here. So that's very easy. So now this is my function, like f of x, y is equal to 2x squared plus 2y minus 25. Yeah, that's like my function. And what is partial f with respect to x? So partial f with respect to x, that is equal to 2x. What is partial f with respect to y? Because remember that's constant, so that will go away and that will go away. Here, what's my y square? Right? This is like y square. That will be equal to 2y. So what is this guy? So that would be like dy over dx. That would be like minus 2x over 2y. And that would give me minus x over y. So you see, I got the same answer, but this is much easier. Yeah. Using. So that's why I thought like not a bad idea to cover this, so that if you want to do this in the FE exam, you will do it the easy way, not this way. I mean, this will take you, I don't know, 5 minutes. This will take you 1 minute. Yeah. So here I give you like another problem to practice. We did this before. Remember, we did this using partial derivative without like implicit differentiation. So this is equation of the sphere, and if you look in the previous video, you will see that we did this like, so we said like z, or express like we said, z is equal to something like this, the square root of 9 minus x squared plus y squared, and then you use like uh, whatever, like you did this just, but here if you use like implicit differentiation, that would be much easier. So I will show you this when we do the tutorial in the practice problem, and again these tutorials are optional. So here, like try to do it using partial derivative, what we did before, and using implicit differentiation. And so here, this is the solution. So this is with partial derivative, this is with implicit differentiation. Okay. This is again more practice for FE exam. So FE exam, you get these type of questions. So I put it again. Try to pause the video and do some practice, FE exam practice, and then you can run the video again and look at the solution. So the solution is this. So here, without partial derivative, it would be very difficult to solve this guy. Yeah. Because yeah, so that's like here, if you use any other technique, that here explicitly in an equation like this, you need to use implicit differentiation. So implicit differentiation is not just easier, but in some cases, that's your way to solve this problem. Yeah, that's why I wanted to cover it so that you be well prepared to FE exam. Uh, this is your homework problem, and this homework problem is very similar to this problem here. This is what I usually do. And if you want to know how to solve this problem here step by step, please watch the tutorial. And this tutorial will give you an idea of how to do this guy. But again, this is like the important part is here. This is like what I want you to learn from all this. Total derivative represents the rate of a change. So that's the main concept that you should be learning from this lesson, basically. Total derivative represents the rate of a change of a function with respect to vari one variable, considering indirect change through other variables. So basically, I'm f of x with respect to x, but here I'm considering the changes from all other variables are accounted for. Yeah. Versus partial derivative represents the rate of a change of a function with respect to one variable, also like df f partial x, while keeping all the other variable constant. Yeah. So here all the other variable are basically like working, like you see the impact of all the other variable when you do this guy versus this guy, you hold them constant. So thus total derivative account for all passes of variation, while partial derivative isolates the effect of a single variable. That's the main thing. Okay, so let's close with this. So this is your homework question, conceptual understanding, and I'm asking you here which of this statement is true. So try to pause the video and read it and see like if you can get the right answer, and then I will show you like the right answer. I will answer this question for you. That would be a bonus for those students who are watching the video. So I would know who's watching the video and who's not watching the video. So if you're watching the video, I'll tell you the answer and you will not get it wrong. Yeah. If you're not watching the videos, then you will get it wrong, and I will know that you're not watching these videos. Okay. So which of the following best describes the difference between like total derivative and partial derivative for a multivariate function? So let's go through these guys one by one. Total derivative only measure the change in one variable, while partial derivative measure a change in all the variable. Actually, this is the opposite. So this is the opposite of the truth, because partial derivative focus on one variable, while total derivative consider like implicitly like the impact, like the change from due to all variables. So this is wrong. Yeah. So this cannot be the case. Okay. Let's look. So this is wrong. Partial derivative keep other variable constant, while total derivative consider how variable change together. So that is, yes, so this is like keep all the other variable constant that isolate one variable and see the effect of this one independent variable. Like, so I keep y constant and I see how like my height is changing with x. While here, total derivative, it consider how all variable are changing together. So I will see how, for example, x and y are changing and they are maybe a function of time, and like how all these are like, for example, like changing together. Yeah. So this is the correct answer. Let's look at this one. Total derivative measures the slope of a tangent plane. Oh, that is a little bit tricky. While partial derivative measure slope of a curve. Uh, this is true, like partial derivative will measure the slope of a curve, yeah. Partial slope of a curve. So partial derivative will like measure slope of tangent line to a curve by holding all the other variable constant. So the slope of the curve. Yeah, so a tangent line on the curve. While total derivative can be treated as like tangent plane, especially define it, it's more accurate to say that it describe like changes along a path, not necessarily like not specifically. So this is somehow inaccurate because I would say it like total derivative can be related to tangent plane because it defines it, yeah. But it's more accurate to say it just describes a change along a path. Okay. And while partial derivative measures the slope of yes, the slope of a tangent of a curve holding all other variable constants. So this is maybe so this is not very accurate. This is more accurate. Yeah. Let's look at the other one. Total derivative depend on the implicit differentiation, while that's a good one. I like this one. Total derivative depend on implicit differentiation, while total derivative does not. Total derivative does not inherently depends on implicit differentiation nor partial derivative, because implicit differentiation, this is just method for a solution method. So partial derivative can sometimes involve implicit differentiation, as like in the sphere example, for example, but it is not a general requirement. Total derivative does not inherently depend on implicit differentiation, because I showed you some of this total derivative method and we solve them without implicit differentiation. So implicit differentiation, like the need for implicit differentiation, arises from the way the function is presented and has nothing to do with the type of derivative being calculated. So this is more like a math type of thing, solution method, while partial derivative like dz with respect to dx total and total derivative dz with respect to dx. This is a type of derivative. This is a partial derivative. This is a total derivative. Implicit differentiation this is just like a solution method or one way solution method. Okay, so basically, so the correct answer, so this is also wrong. So this would be like B would be the correct answer. So you can choose this one. Okay, for your homework. Okay, so I think that is it for